Okay, so what is about this tutorial? We are going to look for what I believe, according to my experience with several customers, is the best way to deploy IPv6 in cellular networks. I will do at the end also some considerations about applying the same technology to other kind of networks, I mean non-cellular, so GPON or DSL or whatever technology, access technology you use, okay? So, looking at the cellular networks today, I think everybody have a clear view that we really need to support IPv6. We have exhausted IPv4. So yes, of course, we can use carrier-grade NAT. We can use sharing of IPv4 addresses. But that means basically we provide less ports to every user. And today, new applications are using more and more ports, so that's in contradiction, right? So if we reduce the number of ports, but applications every day use more ports and users every day open more applications at the same time, even just browser windows or things like Google Maps and so on, they require lots of ports, right? So it's not a good way to go. We have also continuously increase in number of users, so that's another reason for having more need for addresses. And also we need to remember that what happens is that even if you are using a smartphone, it's more and more common that the people is using tethering to provide connectivity to other devices. So again, the same problem. You have a single IP address shared among different users, reducing the number of ports, how you are going to support more and more devices being connected by tethering to this network. One more reason, which today is not very common in cellular networks, but I am sure it will become, because with new technologies like 5G, you will have up to 1 gig capabilities and probably even more in the future. You can have, by the tethering network, devices that run virtual machines, okay, or applications that run on something similar to virtual machines that also require one address at least for each one, okay? So again, you look for whatever position you look, you are asking for more and more addresses. New technologies like voice over LTE, IMS, Internet of Things, no way. You really need to go to IPv6. I think that's clear for everyone. And what I am trying to define here is a long-term strategy. I am not looking to suggest you deploy now carrier-grade NAT and then later on change to something else. That don't make sense. Let's do our end goal now, if we can, instead of doing that in several steps, right? So, do you think dual stack is the best solution? If we have the one in the middle, the box in the middle, if we have an end user equipment, a cellular phone, a smartphone, being dual stack, that's the best way. This device can connect to both IPv4 and IPv6 devices. Do you agree with that? Yeah? Not really. If we don't have any more IPv4 addresses, we cannot do really dual stack, right? Do you have enough IPv4 addresses today for your users? And for tomorrow, you can keep growing, considering dual stack approach. What is the cost, I mean operation and management cost of having dual stack? It means you are managing actually two parallel IP networks, IPv4 network, IPv6 network. It means when somebody is calling your call center needs to be able to support issues related to the IPv4 network and the IPv6 network. What about performance? I'm not going to talk about performance right now, but wait later on, you will see how different is the performance in IPv4 and IPv6 networks, okay? So you can take your decision about what performance you prefer later on. What about licenses? Sometimes you need to pay for some elements in wireless networks, in cellular networks, you need to pay different licenses for V4 or V6, or if you want to run both of them, okay? What happens if you have in every device multiple address stacks or address families like IPv4 and IPv6, which authentication those two addresses? Some applications rely on addresses to authenticate. So if you're having two of them, it makes more complex, and sometimes it fails. So there are different issues on that. So what alternatives we have which are not dual stack? Well, we can go through IPv6 only. We can go to IPv6 only with NAT64. We can add to that DNSSEC. We can have 464 XLAT, and we can consider other transition technologies. I am going to talk in the next slides about each one of those. So let's consider IPv6 only. There are many examples of content providers already doing that. I think the most well-known, because they did a lot of presentations, is Facebook. Facebook started in 2014 deploying IPv6 in all their network, and at that time they have already 90% of his traffic being IPv6 only. We are not talking about a small amount of traffic. We are talking about more than 100 terabits per second, which is a huge amount of traffic. I am sure nobody of you, or even all us together, can reach that traffic, right? In June 2015, they have already deployed IPv6 in 100% of his data centers, okay? This allows Facebook to be connected by any IPv6 only device. So if we deploy IPv6 cellular networks, we will be able to reach Facebook. That's fine. The way Facebook is doing, I am not going to enter into the details, you have them on the slide, but the way Facebook is doing to support as well IPv4 users, which still don't have IPv6 connectivity, is somehow like showing on the outside of the data centers through BGP, both IPv4 and IPv6. But inside the data centers, all the traffic is done by IPv6 only, okay? So this way, they support V4 and V6 users, but having IPv6 only traffic inside their data centers. That's the way. And many content providers are going to the same path, okay? So this is clearly one way, and it means, yes, it will be possible to do IPv6 only cellular networks. However, it's not an option today, because the case of Facebook is one, but we have other content providers that have not yet deployed IPv6. So if we deploy IPv6 only in the cellular network, our users will be able to access Facebook, but maybe not other contents, right? Probably many other contents will not be accessible for them. And in addition to that, because the tethering, we can have devices connected to internet by means of the cellular phone that maybe they are IPv4 only, okay? So again, let's suppose you have a printer, a network printer, and it's an old one, and you want to access it by means of your cellular phone, and you will not be able to access it, okay, because it's IPv4 Or you have IPv4 older cameras, and you want to share your network connectivity to show somebody what the camera is recording, and you will not be able to do that. So IPv6 only in the cellular network today is not a valid solution. So let's look to one of the possible transition mechanisms we can use, is NAT64. NAT64 is a way for IPv6 only devices. Let's suppose that we have an IPv6 only cellular phone to connect to IPv4 only contents on internet. So this is precisely what we are asking in the previous slide that we cannot do, right? So it seems like a solution. We had a previous transition mechanism, which was NATPT, that was trying to do the same, but it didn't work it very well. And in IETF, we decided to deprecate that mechanism, so it's not longer valid. The idea is that we can have several IPv6 only devices sharing a single public IPv4 address to access the IPv4 internet. In fact, in a provider, this is done by sharing a pool of IPv4 addresses among many, many users, okay? That's the way NAT64 is working. So basically, NAT64 allows that the cellular phone, which will be IPv6 only, will translate the packets into IPv4.1 to reach a content provider which is IPv4 only. And then the response to the queries will be converted again from IPv4 to IPv6, okay? Now, I mentioned here the documents from IETF that you need to read if you want to know more about the technical details, but I am not going to go through that. Just mention that the actual specifications of NAT64 are good enough for most of the applications, which basically means it's able to translate TCP, UDP, and ICMP, but only that, okay? In most of the cases, also the people that is using NAT64, the providers that are using NAT64, they add some additional protocols that they support by means of application layer gateways and things like that, okay? So that's possible, but it's not, let's say, part of the standard. It's functionalities that vendors add to their products. Now, how this translation is done, again, I am not going to go very deep into the technical details. Basically, what you need to understand is that we have either what we call a well-known prefix, which is 64:FF9B::/96. As you know, the IPv6 addresses are 128 bits addresses, so if we have a prefix which has 96 bits, the rest of the IPv6 address is 32 bits that we can add to this prefix, okay? So this is the default NAT64 translation prefix, but also the operators can decide to use their own prefix. So we have either the well-known prefix or the network-specific prefix. It's another way to use NAT64. It depends on your network requirements. You decide to go one way or the other. And you can also change the length of the prefix. Usually don't make sense, but here you have a table with the possible lengths, okay? And you have the representation of how you put the IPv4 address depending on the length, and then you need to add a suffix, okay? If the length is different than /96, of course. As I already mentioned, everything out of TCP, UDP, or ICMP is not going to work, okay? Unless your specific vendor is adding functionalities. But today, especially in cellular networks, most of the applications are based on HTTP. So if you have support for TCP and UDP, that's it, which that could be enough, okay? So in theory, everything should work. Even many VPN services are actually today running on TCP or UDP, so that's again not a problem. However, and this is the important bit here, some applications like online gaming, Skype, in general, whatever application that is using IPv4 references for peer-to-peer communication, or any application that is using literal addresses, so instead of domain names, it uses something like 8.8.8.8, that's wrong. You should use the name, not a specific literal address. And there are still a lot of web developers that keep using IPv4 addresses, or all their libraries like socket APIs will not work, okay? So NAT64, it solves the problem if you are using DNS names. So this will be the picture of a NAT64 network implementation. We have access to internet, which IPv4, access to internet, which IPv6. I think there is a pointer here, right? Yeah. But if your network is IPv4 only, will not work. So you have here an IPv6 device, and you have here a dual stack device, and they will be able, by means of IPv6, because our access network is IPv6 only, to access both IPv4 and IPv6 internet, okay? If we want to access IPv4 internet, we need in the device what we call a functionality to synthesize the Quad-A records, because as you know, IPv4 addresses use in DNS A records, IPv6 addresses use in DNS Quad-A records, okay? So if we want to access from an IPv6 only device an IPv4 only service, we need some functionality that converts our A record for the IPv4 destination into a Quad-A record one, okay? So there are some operating systems that have a built-in Quad-A record synthesis. What that means is that they put in front of the IPv4 address the well-known prefix that I described in the previous slide, okay? So that's it, very simple. You just add 96 bits with the well-known prefix or the network-specific prefix, and then the NAT64 is doing the translation. Now, is that going to work? So if we have an IPv6 only cellular network which NAT64 is going to work, well, if the smartphone supports this Quad-A synthesis, yes, it will work. For example, devices like iPhones have a new version of Happy Eyeballs that include this, okay? So yeah, we have devices in the networks that can do that. But for the rest of the cases, it will not work. We have, again, IPv4 only applications, or we have IPv4 only tethered devices that will not work in this situation. So again, this is not the best path to move to IPv6 a cellular network. So different alternative. Let's look at DNSSEC. DNSSEC is a DNS service added to a standard DNS. You don't need something new. Typically, most of the DNS services, servers like Bind or many others, have this functionality that is doing the same I just described, this Quad-A synthesis, okay? So it means the DNS will find an A record and will say, hey, this is going to be accessed from an IPv6 only network. So we need to add the well-known prefix before the 32 bits of the IPv4 address. So we have in total 128 bits of IPv6, okay? So this functionality, instead of being in the device, can be in the device, but also in the network, okay? So if we have this functionality in the network, we will have something like this. So the new thing here is this DNSSEC service in the network, okay? So what happens here is very similar to what we had in the previous slide, but still we have IPv4 only networks or devices. Here I am making a CPE, okay? But it can be also a cellular phone, in fact. No need to have a CPE in the middle, okay? It's the same situation, no difference. So this picture is valid for cellular networks, but also for, I don't know, DSL, GPON, cable, or whatever, okay? If you have a CPE in the middle. So here we have, again, IPv6 only connectivity, and of course, the IPv6 traffic goes through without any help, but when we want to reach from an IPv6 node an IPv4 internet service, we need this NAT64 plus the DNSSEC synthesis, okay? How this NAT64 works? Okay, what happens basically is that the V6 node want to access a device which is IPv4 only, and then it will request for this device the DNS, and because the DNS has this DNS64 functionality with the synthesis, instead of returning the A record, it will convert the A record to a quad A record. So if you look, the hexadecimal of 1920.1 is the same that I have embedded here, okay? So it's just the IPv6 well-known prefix followed by the hexadecimal of the IPv4 address. So then once it has a quad A record, he can go through the NAT64, which will convert the packets from IPv4 to IPv6 and vice versa, okay? That's the way a stateful NAT64 works, okay? So, are we all good? Do you believe that we can do this way IPv6 service for everything? Well, yes and not. The problem is that this works very well if the applications are using DNS. But what happens with applications that still use literal addresses? They will not work, okay? So this is not yet the perfect solution. And again, we have the same problem. IPv4 tethered devices that are using the cellular phone as a CPE to connect to internet will not be able to connect to internet because the cellular phone has only IPv6 only access, okay? So if I go back, remember that here the connectivity is IPv6 only, okay? That's the important thing here. We want to get rid of dual stack in the access network because having dual stack means having IPv4 addresses, which we don't have anymore, and managing two networks, which is an extra cost. Okay, so remember that's the key point. We want to have IPv6 only because we have no other way. If any vendor tells you, yes, you can keep going with dual stack, change your vendor. They are lying you. That's clear. They don't have the right solution for you, okay? So again, NAT64 with DNS64 is not enough. So look at this. This is an old table. It was compiled by T-Mobile, one of the bigger mobile operators in US. And they compared all the applications that break with NAT64 and DNS64. So for example, just to name a few of them, Skype, Spotify, Last.fm, Netflix, Google Talk, Google+. So it's nice. The applications that most of the people use are not going to work, right? So do we really think we want that? Obviously not, okay? We need to provide IPv6 service in a way that the users don't notice any change. Everything should work for them, okay? So we have a new solution, which is what we call 464XLAT, and everything is working with that new protocol. And we are going to describe how this protocol works. 464XLAT is actually not, let's say, a new protocol. It's just picking up existing protocols and making them work in a different way. So what 464XLAT is doing is sharing IPv4 addresses, but instead of fixing a number of ports for every user, it's dynamically allowing the users as many ports as they need, okay? So if you have a pool of IPv4 addresses to share, basically, as soon as applications in every user need more ports, they get allocated more ports. So everything works, there is not a limit. The limit is basically how many users you have and how many addresses they need in total, including the possibility of 65,000 ports that they have, okay? So this means a much more efficient way of sharing IPv4 addresses than carrier-grade NAT. It's a way to grow your network not being tied to how many addresses you have. Because in carrier grade NAT, you say, okay, let's give every user 2,000 ports, so you have only 30 users for every IPv4 address, okay? In here, you can deploy IPv6 as more users access contents which are available with IPv6, you have less and less usage of a more efficient translation mechanism for IPv4, okay? So what 464 XLAT is doing is offering the same basic service, which is TCP, UDP, and ICMP, plus whatever is supported by the vendors, because as said before, sometimes support more features that are not standard, but they are being supported. And it means everything works, okay? So that's our final goal. We want to deploy IPv6 only, but we want to make sure that nothing will break, okay? With 464 XLAT, you don't need to do strange things like you do in carrier grade NAT and other transition mechanisms like deep packet inspection. So you have a more efficient way to keep doing traffic engineering if you need that. It's something which is in cellular networks very well supported. I will talk about different platforms of cellular phones later on and how they are supported in both commercial products, but also open source, okay? So this is how 464 XLAT is working. Look, we don't have anymore the red cross here. So it means with 464 XLAT, this is also working, okay? So we have no issues here. Never you have an IPv4 only network or device, neither you have a dual stack. Even having, like before, IPv6 only access network, everything is going to work, okay? So how it works? We have here what we call the plat, which in fact is the NAT64 plus the DNS64. Okay, all together are in the scope of 464 XLAT named as plat. But you can think, like in 2 slides ago, as 2 boxes or 2 functions: NAT64, stateful NAT64, and the DNS64. Both together configure what we call the plat. And we have at the CPE or at the smartphone, we have what we call the CLAT. Let's see what they mean. Here you have a better picture, and it shows that CLAT stands for Customer Side Translation, and PLAT stands for Provider Side Translator, okay? So if this is a cellular network, never mind again this is a smartphone or a customer premises equipment, a CE or a CPE. Basically, you can have here dual stack applications. The ISP network is IPv6 only. The ISP network is connected to IPv6 internet, but also to IPv4 internet by means of the plat, okay? And then if an application is working with IPv6, it goes through straight, no translation at all. But if the application is using IPv4, it can go through the translators, okay? Now, we are not saying it's going to the translators all the time. Let's see how it works. One more detail is, of course, the CLAT is doing stateless 4 to 6 translation, and the PLAT is still doing the same as NAT64, the stateful 6 to 4 translation, okay? So let's see this. 3 possible situations. Let's suppose we have a dual stack application that is running IPv6 to connect to IPv6 only internet. Because we have IPv6 only network, of course it works. Nothing to change, right? So we have IPv6 end-to-end. That's the optimal situation. Now let's suppose we have a dual stack application that is trying to connect to an IPv4 only device. What it happens is the same as we mentioned before with NAT64 and DNS64. The device will try to connect using IPv6, but because this is IPv4 only, we'll need the well-known prefix or the network-specific prefix to synthesize the quad-A record and being able to be translated by the NAT64. Okay, so we have one level of translation. Why this is possible? Because it's using DNS64. Because the device here that we are trying to access has a DNS name. But remember that what we said before is that what it breaks is when we are not using DNS, when we are using older SOC API or literal addresses, right? So that's when CLAT takes his function. So when the device detects, when the operating system here detects that instead of DNS, there are literal addresses, it will do a translation from 4 to 6. So that literal address can traverse using IPv6, the IPv6 network, the IPv6 only network of the ISP, and at the edge, get translated again to IPv4. So end-to-end is like we are not doing anything. We are translating twice to avoid breaking that, okay? Everybody see the point? If you have questions at any point, don't wait to the end, just raise your hand and we try to answer the question, okay? So, 3 possible cases again. We have IPv6 end-to-end, everything is perfect, this is the ideal situation, this is what we want to get at the end, to get rid of completely IPv4, but this may take a few years, of course, because there will be some people that will be still connecting to their, let's say, web servers or whatever services they have with IPv4. Second situation, we have dual stack applications that connect using the NAT64 because they use DNS. Okay, so here DNS64 is helping. Or those applications that are broken because an application that use all APIs or that use literal addresses basically is a broken application. That's a problem from the developer. The developer should have never used literal addresses, but they are still doing that, unfortunately, okay? Now, what is the approach from different vendors here? Android and Windows, in the case of cellular phones, they already have the CLAT built in the operating system, okay? So it means any Android or Windows smartphone will work here. Instead of that, Apple decided to make something quite unique, which I like very much. Apple said, I am the big boss. If you want to have your application in my App Store, you support IPv6, or I kick off your application. Okay? So what that means? They don't have the CLAT because they don't need it, because everything is IPv6. So it's working here or here. Okay? So obviously it's much more efficient the way Apple is doing, but it's forcing the application developers to make sure they support IPv6. It's more looking at the future. It's making sure the future is here now instead of 5 years after, okay? Obviously, it's the best way, but for whatever reason, that's marketing, strategy, commercial, I don't know, Android is not doing that, okay? If Android was doing that, we will have, we, the service providers, a better life, but it's not happening, okay? So this is the difference between the two platforms, either having CLAT, which means that applications can still be the old way, broken, basically, or having no CLAT support. But what Apple is doing is something similar to CLAT for not just for the smartphones, but for the laptops and for the tablets and applications that don't come from the store, okay? I think, well, for the tablets, actually not, because I think that the applications for the tablets are the same as the ones for the smartphone. So it's actually only for the laptops or for the Apple desktop computers, okay? So, if we look into the details of this CLAT conversion, including an addressing example, we have here, it's not easy for me to hear. Let me, do you have a hand microphone? Okay, here I can see it better. So let's suppose we have this device with this address, 192.168.2.3, okay? And this device wants to access this server, which has address 203.14.147. So what happened is that in order to make the CLAT work, you need to define what we call the source prefix, okay? I am using here a documentation prefix to make the example. So it's 2001:DB8:ABCD:/96, okay? The default size for that. Now, the destination prefix, we are going to use the same, but 1, 2, 3, 4. And then what happens is that the source address, it gets embedded in the source prefix. You see, ABCD, ABCD, then the source IPv4 address. So that's an IPv6 address. It's just adding the prefix to the IPv4 address. So that gets translated, and then you have also at the translator here an equivalent prefix, and it gets translated to 192.1.0.1.0, and the same for the destination, okay? So once you have those two IPv6 addresses, it just works. So from source IPv4 to source with IPv6, that's the first prefix change, the first address change from 4 to 6, and then from 6 to 4, okay? And the same for the destination. So that's what we get here. Everything translated from one side to the other, okay? It's a very simple example. I am writing it in decimal, so it's easier to see, but of course, at the end, all this is hexadecimal in reality, okay? Let's see. Okay. So, this is basically making it simple. If you look at a cellular network, you will have the device here. That's the user equipment. So the user equipment has the application without support for IPv6, and then it has the CLAT. The CLAT basically is a small C code. This size is like 20 lines of C code, which is a daemon. It's looking at the packets, and only when it detects literal addresses is going to perform his functionality, okay? So it's very small code, it's not a big implementation, nothing really complex. Then we have the wireless network, which is IPv6 only, and then we have the provider service in the cellular network as well that has the PLAT, okay? The conversion again from 4 to 6, sorry, from 6 to 4. And of course, at internet, we have this IPv4 only service. Questions up to here? Anyone? Keep going? Okay. So availability and deployment of this technology. Well, as I mentioned, this technology has several pieces. One is the NAT64, another one is the DNS64. The DNS64 basically is supported in any DNS major provider. So if you look at Vine or whatever provider you are using for DNS, they have this DNS64 functionality, okay? So that's done. If you have DNS appliances, they are usually based on Vine or other kind of DNS servers, so they also do the same. In terms of NAT64, there are major providers like Cisco, Juniper, F5, A10, Huawei, NAC, and there are also open source tools. Okay, so you can have your own NAT64 box by having, for example, Ubuntu, which a tool which is open source, which is Joule. That's the one that I like more. Okay, there are others, but my preference in terms of scalability, performance, functionalities, etc., is Joule. Joule is developed by NIC Mexico. Okay, so it's you just type joule.mx and you find it. So it's a very useful thing that performs a lot of functionalities. Then we have CLAT. The CLAT, as I mentioned, is supported in Nokia, in Windows, in Android since version 4.3, so that's several years ago. NAC, Linux, Joule, OpenWRT, because as I mentioned, this presentation is basically for cellular, but the 464xLAT works also in residential networks, okay? So that means that the CPEs need to support the CLAT. There are very few CPEs supporting CLAT right now. We had a panel with vendors 2 days ago, and they confirmed that they have implementations, but they are not right now having it in the devices that they sell, but they could do it any time. And I am actually working in ITF, in V6 working group, to update the documents that have the requirements for the CPEs to have this included as a standard, okay? So it will come. I really think that if you are deploying IPv6 in a residential network, you should ask your CPE provider to have support for CLAT. If not, look for an alternative vendor. There are a few. NAC is the only one right now that have it in commercial products, I think. And then I mentioned Apple. Apple is not having the CLAT support, but they have a similar functionality. They actually don't need it because they are mandating support for IPv6, but even though they have something just in case, okay? If an old application is still not updated, blah, 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 well, you have this. Apple didn't took the decision to mandate for IPv6 from one day to the next one. It was not an overnight decision. Apple announced this about 2 years ago, and Apple provided 1.5 years to the developers to do that. It's more than enough, okay? I know cases for applications. For example, one of my customers is a big group of banks, financial institutions, and of course they have online payment applications and all kind of things. And they received a letter from Apple a few months ago telling you have 15 days to update your apps or they will be dropped from the App Store because you got 2 years already, okay? So if you have customers developing applications and they have not yet received the letter, better tell them so they don't have, after all, just 15 days. Because many developers are missing this. I don't know why, but they are not paying attention or they don't care or whatever, but it's going to happen. Regarding commercial deployments of 464xLAT, well, there is T-Mobile. T-Mobile had, the last figure I saw was more than 70 million users. What that means? It means that just with T-Mobile, this mechanism, 464xLAT, is the protocol that has more IPv6 users in all the world. Just one protocol, just in one provider, has much more than all the other transition mechanisms together, okay? That clearly shows that this is the right way to go, obviously. But you have other providers like Orange in several countries, Telstra, SK Telecom, I think that's South Korea, and there are a few others. I am doing myself some trials and some big deployments in Central America and South America, so there is a lot ongoing with 464 XLAT. It's not something new. It has been already in the market since 3 or 4 years ago, so it's done. Now, one thing that you need to consider when you do your deployment of 464 XLAT, or actually when you use DNS64, because it's not a 464 XLAT problem, it's a DNS64 problem. DNS64 changes the DNS answers, and of course, DNSSEC has been designed to detect such modifications. So DNS64 can break DNSSEC. And I say can because, of course, there are as well solutions for that. You need to do the deployment correctly to avoid that problem. In general, the DNS servers which a DNS64 functionality, like for example bind, by default will not synthesize the Quad A responses if the DNSSEC OKDO flag was set in the query. In this case, because you are getting only an A record, it means that the CLAT will take the responsibility, as in the case of a literal IPv4, to keep the traffic flow end-to-end as IPv4. So you don't break DNSSEC. What that means basically, it means that even if you could, for DNSSEC A records, use just NAT64, if you do that, you will break DNSSEC. So instead of that, it's better, in those cases, do a double translation to avoid breaking DNSSEC. This is automatic if you set up your network correctly. So it's not something you need to take care case by case. It's not something you need to find what DNSSEC destinations I have in my network. No, not really, because that will be impossible. It's something that you need to configure properly your DNS64 box to do that, okay? Today in cellular networks, this is typically not a problem because cellular operating systems in general don't support DNSSEC. But in a cellular network, you may have either applications that add DNS support on top of the operating system, or you may have also, for example, a laptop which requires for whatever destination DNSSEC using a tethered network. So you need to take care of this even if the smartphones don't support DNSSEC by default, okay? So just pay attention to that detail. And the last possibility, let's look for other transition technologies. Well, we have 6RD, we have DS Lite, we have lightweight 4/6, we have MAP-E, we have MAP-T. There are many transition technologies. Some of you probably know already some of them, or you have been in the tutorial, in the transition tutorial that Philip did the first day. So you have already some of them in your mind probably. No way. No way, because basically they have never been implemented in the smartphone operating systems. So even if you are willing to use in your cellular network any of these applications, are not useful, okay? Of course, the reason for that is because some of them, like 6RD, require using lots of IPv4 addresses. So again, this is the problem we are trying to solve. So if you need IPv4 addresses, you don't want to use IPv4 addresses. They usually take a heavy network setup which 464 XLAT don't require anything special. We will see later on the details that we have for 464 XLAT deployment. They require the HCP, which typically is not used in cellular networks. And of course, I already mentioned that because 464 XLAT is using NAT64 and NAT64 has more advantages than carrier grade NAT in terms of how it's multiplexing the IPv4 addresses and ports, it means you have more advantages with 464 XLAT in terms of less consumption of shared IPv4 addresses, right? Okay, so that's a clear advantage. Now, I mentioned at the beginning that one of the advantages of having IPv6 only networks is performance. Look at this slide, which is coming from Facebook measurements. It's a little bit old, but it's the same today, or even maybe better. It's from March 2015, and it's measuring the performance of both IPv4 and IPv6, time to complete an HTTP GET in both iPhone and Android, okay, in a cellular network. So let me go there. Yeah, okay. So this is an iPhone, okay? And look, this is IPv4 performance, and this is IPv6. The improvement is 30%. So the performance, the user experience in terms of how much take to complete an HTTP GET is 30% better with IPv6, okay? That's a lot. If you look at the same in Android, this is 40%. Now, why Android performs better? Well, because it seems that the first implementations of the IPv6 stack in iPhone were not performing so well. So what Facebook did to get also in iPhone 40%, they decided not to use the IPv6 stack from Apple, and they included what they call mobile precision, which is their own implementation of an IPv6 stack in the Facebook application in iPhone. So when you get, at least in 2015, I am not sure if that changed lately. I could check, but I never remember to check. I always do this talk and always forget to check later on with Apple. So what happens is that when you download the Facebook application in an iPhone, it comes with a built-in IPv6 stack and is not using the stack from the operating system. And then it performs the same 40% better performance than Android, okay? Compared with IPv4, of course. Is not that a good reason to go to IPv6? 40% improvement. It's not just the cost of your network, it's radio bandwidth, it's a lot of things, and it's user experience clearly, okay? And that's what you want to get, better user experience. Again, questions? You can use this
one. Excuse me, I don't exactly understand the figure. So does it try to show the performance when both the smartphone and the content provider are dual stack, or one of them are v4 only?
In this case, never mind if they are both dual stack or the iPhone, for example, is IPv6 only. Okay, the point here is if you try to compare how much time it takes to get, here is very small, but you can read it, time to complete an HTTP GET, okay? If you do that test with a dual stack phone to a dual stack service, and you try first with IPv6 and then try with IPv4, IPv6 will be 40% faster to complete the HTTP GET. It don't mean speed, it means time to complete the GET. Okay? Is that your question?
Yes, that's my question. But I believe people will challenge if both are dual stack and then IPv6 is native.
Yes.
IPv4 is also native. And IPv4, I believe the packet will be shorter. And then how come?
Yes, IPv4 is 20 bytes and IPv6 is 40 bytes header.
And then how come?
Because in IPv4, everybody need to share addresses because you don't have addresses. So you have carrier-grade NAT and maybe several of them. And that consumes time.
Okay, so the 40% delay of IPv4 is quite
in part maybe because carrier-grade NAT, in part. In cellular networks, sharing addresses, carrier-grade NAT has been there since the beginning almost, okay? So most of it probably is carrier-grade NAT. I didn't look at the details of the study or even if they studied where it comes this delay, okay? Or this improvement, look at the other way. But definitively, it means also the stack maybe is better with IPv6 than with IPv4. Maybe there are many, many reasons, not just one. But one of them may be definitively, this is extra cost for the carrier-grade NAT. Okay, so what about the cost? I mentioned also in the first, I think it was the first or the second slide, something about that. Deploying this transition mechanism 464X-LAT and having an IPv6 only network basically, or access network, means you don't need to buy carrier-grade NAT. Yes, you still need to buy NAT64, but I already mentioned that NAT64 scales better. So maybe for a big network, you need 5 carrier-grade NAT boxes. And if you need 5, you will buy 10 because you usually want to have high availability. So you will buy double, or maybe not double, but instead of 5, you will have 6 or 7 boxes, right? While in NAT64, because it scales better, you will have less boxes. Instead of having, let's say, I am just making up this number. I didn't try it because it depends on the equipment, the vendor, and so on. Let's say you have 100,000 users, which is a CGN, which is a carrier-grade NAT box. Probably with NAT64, you can have double number of users, okay? Again, this is just numbers that I am making off right now. It's an example so you understand the scalability. And of course, you will need less IPv4 addresses for NAT64, okay? And again, you will have all the port numbers, while in carrier-grade NAT, you restrict the ports per user. In addition to that, there are no implementations, at least what I know, of carrier-grade NAT in open source. But for NAT64, you have, for example, Joule, okay, which is open source, and you can use in your network. So you can buy very big servers and build your own NAT64 boxes. You don't need to buy the boxes from a vendor, okay? So you can save a lot of money there. Again, you don't need to buy IPv4 because with your existing IPv4 addresses, probably you can handle much more users that if you go to carrier-grade NAT and you need to buy more addresses. You can do what we call a progressive deployment. You can, for example, say, let's provide IPv6 service to with 464X-LAT to new phones, okay? And then you are not impacting existing users, and you go naturally increasing the number of users according to your growth in IPv6 traffic. And that means that your IPv4 traffic is decreasing, okay? So as more content providers have support for IPv6, as less IPv4 traffic you will have. What about billing? One of the most complex things in any network, especially in cellular networks, is billing, right? So some people believe that they need to buy a completely new billing application to support IPv6. Or maybe they need to pay for an upgrade of the application they have. Or maybe it has been developed in-house. And maybe the developer is not at the company and they don't know how to take over. Okay? That happens. Everybody knows that this happens. Sometimes developers don't document very well the application, so trying to look at the application again after 5 years or 10 years, it's a complex thing. Well, this is not a problem, because what you can do is two alternatives, or maybe a combination of both of them, is trunking IPv6 addresses in CDRs, in the records, in the call records, okay? Or the alternative is to hash the IPv6 addresses into IPv4 records. So you can have something in front of the billing application to take care of this. So you will actually not need, let's say, overnight a solution for that, because you can patch that in a very easy way, okay? Roaming. You can enable IPv6 inside your network, but at the same time, you can use what we call policy and charging control function to enable in a selective way which roaming customers get IPv6 sessions, okay? What that means, basically it means that depending on which country your users are moving, they will get IPv6 service or not, because maybe your roaming partners have that or not, okay? So you don't need to actually tell the customers you need to change your APN or anything like that. If you are roaming, that will be automatic, okay? There is as well an ITF document, which is 7445, that is doing an analysis of failure cases when IPv6 is in roaming scenarios. So you can look at more details about that. But basically, the most simple way to solve them is this policy and charging control function. Okay? So for those that have already knowledge of 3G networks, I'm not sure how many people here. Maybe it's a question that I should have asked at the beginning, but not everybody was here at the beginning. We are maybe talking about very specific details on 3G networks, but it's not difficult. And just in case, because what we have talked up to now is precisely all the things related to IP, okay? But let's take a look without entering into too much technical details, because I am sure here some people has no knowledge about IPv6, about cellular networks. Let's take an overall look about how a cellular network works. So basically, in a cellular network, we have what we call the user equipment, which is the smartphone in our case, or it may be also a cellular router or a cellular modem or whatever you want to call. You have the radio network, and then you have the domain where all the transactions to connect the user equipment take place, and of course, the provider, the ISP provider. In our case, we are targeting to an IPv6 only provider, which of course needs to be connected today to both IPv4 and IPv6 internet. There are different devices. I am not going to read across them. You have the details in the slide, but I am going to look into what is more important in terms of deploying IPv6, okay? Some additional details that you need to know is that in cellular networks, there is a user plane and a transport plane, and they could run different IP versions, okay? So that's not a problem, because there will be specific tunneling protocols that do that over the radio network. The other interesting aspect or important aspect is that in order to transport the user IP packets across the cellular network from the user equipment, from the terminal to the destination, we need to establish what we call the packet data protocol context. Okay, so the PDP context is the main thing to create those tunnels across the cellular network. Okay, and in order to create those tunnels, this PDP context, we need something that we call the APNs. An interesting thing here is also that this PDP context can be IPv4 only, IPv6 only, or it could be dual stack. So to have IPv4 support, of course, you use an IPv4 only PDP context, which is called IPv4. If you want to have IPv6 only, which is our target, you will have IPv6 only PDP context. And to have dual stack, you have two ways. You either have two PDP contexts, one for each stack, which means using two licenses, because usually you pay for the PDP context licenses to the vendors, or you can have a pure dual stack PDP context, which is called IPv4v6. Okay? 464xLAT has the advantage that it's working with IPv6 only PDP context, because we already said that our end goal is to have an IPv6 only network. So again, this is one more advantage for 464xLAT. You don't need to support for all the cellular phones dual stack PDP context. But you may have that for some of them. Okay, you have in the network maybe older phones that they need dual stack, and you can keep that. Now, I just mentioned that we have this thing called the APN, which stands for Access Point Name. The APN is a logical name referring to one of the elements for the connection of the IP sessions, right? The APN is also identifying external networks. The APN basically is a fully qualified name. So all PDP contexts, at PDP context activation, this device that terminates the PDP context performs a DNS query to find out the names serving the APNs, okay, that are requested by the terminal. And then the DNS response contains the addresses of the devices they need to connect. Usually, there are several of them, so they are selected by round robin. So that's something very standard. Even if you don't know about cellular technology, you can understand what is round robin to have several of them. So what is the correct way, according to my experience, to have the APNs? There is some people deploying IPv6 that uses several APNs. Maybe one APN for older IPv4 only phones, another APN for dual stack phones, another APN for IPv6 only phones, and so on. My experience, and this is the way some networks, some of the bigger networks are doing, for example, T-Mobile in US, is having a single APN for all the phones. Okay? So whatever is the version or the type of terminal that is connecting to the APN, what happens is that this single APN is supporting both single and dual stack. So the cellular IPv6 deployment can be done in such way that is the terminal the responsible to say what he needs. So you don't actually need to configure different kind of terminals in different ways. The APN will respond to each terminal depending on what the terminal is requesting. So it's totally automated, okay? That means it facilitates a progressive deployment. What it happens is that you can start saying, oh, there is a new Android model from vendor X. Let's give this product, this new phone, this APN information. Let's give, for example, just IPv6, and that's it. And when you decide to do that with more phones, you keep going, and then you can even, what they call over-there, upgrade the older phones with the new configuration. So at the end, what is making your life easier is that instead of depending on having multiple APNs, multiple boxes across the network, having different configurations, you basically say, who you are, that's what you need to connect to me, okay? Depending on the device, you get a connection. How we do that? Well, for doing that, there is a very important document from ITF, which is RFC 7050. So this document means how the DNS is responsible for allowing this. And this document describes how is the discovery of the IPv6 prefix being used for the IPv6 address synthesis, okay? So depending on the DNS or the connection from the user equipment to the DNS will need to respond to provide the information for IPv4 only, dual stack, or IPv6 only, okay? So you don't really need to have multiple configuration. It's just responding to what the user equipment is requesting. One more step. We have 10 minutes. I think we are perfect in time. How IPv6 addresses are allocated? Well, by default, today, all the cellular phone operating systems are using a stateless address auto-configuration. This has been described in specifications for cellular networks a long time ago, and means basically every PDP context get, by default, a single /64, okay? It's possible to use in cellular networks also DHCPv6. However, today, most of the terminals, most of the user equipments don't have support for DHCPv6, so it's not in general being used. It will require a relay agent, but the problem basically is not the network. The problem is basically the operating system vendors, especially Android. They don't want to do DHCPv6. Okay, so that's quite challenging. It will provide many advantages, but well, that's life. This is the way we are doing right now. There is also another way, which is a specific GPRS setup, but I am not going through that one because people is not using it in general. So this will be the way a stateless address auto-configuration, Slack, works. If you know about the Slack in other networks, default Slack in IPv6, there is no change, okay? So the user equipment is activating the PDP context, and then all goes through with the request of the address auto-configuration, okay? So nothing special here, different than the standard Slack. Now, if we do a single /64, how we do tethering? Well, there is another ITF document, which is 7278, which explains how you can extend the /64 that you get in the PDP context to the rest of the devices in a LAN network, let's say hanging up from the smartphone, from the cellular device. So basically what it's doing is switching the user equipment, the cellular device, to behave instead of just as an IPv6 host, it turns into a hybrid IPv6 host and router, okay? So the cellular phone becomes also an IPv6 router, so easy. If the user equipment is also having CLAT support, it will as well provide IPv4 service with private IPv4 addresses to the tethered devices. So you need to think at the user equipment as a CPE for the tethered network, okay? It's like having a small router inside of your smartphone. In fact, there are today smartphones which are much more powerful in terms of performance than many CPEs that we have at home. So it's quite a natural thing, okay? If you go for the DHCP way, again, you look at IPv6 DHCPv6 and it's the same. There is no difference, okay, in the way it's performed in a cellular network. But as said, today, this is not supported by cellular phone operating system vendors. So today, I will not recommend to go this way. When you go this way, let's suppose in your cellular network, in addition to connect to cellular devices, you provide service to broadband users with routers, which let's say LTE routers. Then you need to go through this, okay? The LTE routers should support this. Otherwise, you can only provide a /64 to a broadband user. And the recommendation for a broadband user is a /48. So you only can provide a /48 if you are using DHCPv6 prefix delegation in the cellular network. Now, if you do that, the way this broadband CPE or LTE CPE gets connected with DHCPv6 usually is getting for the one link the first /64 of the /48 provided to the broadband CPE. And for that, we have one more IETF document, which is 6603, which basically says, hey, you are a broadband LTE router. You get for your LANs a /48, but the first /64 for this /48 is for your one link, for your point-to-point, okay? So please don't use it because you will create a conflict. That's what this RFC is meaning. And I think that's the last slide. If you have done, well, not the last slide, I have two more, but the last slide on cellular, if you have done IPv6 deployment in your cellular network, you can declare success because you will see that all your IPv4 traffic is moving to IPv6. If most of your users are typically at least 50%, sometimes 60, 70% using YouTube, Facebook, Netflix, all these kind of things that are already supported with IPv6, it means most of your traffic will be IPv6, so you will use less and less IPv4, which means less and less IPv4 addresses. And the most important thing, your customers will never realize that they have been switched to IPv6, okay? Because they don't need, if you have a single APN, they will not need to do any change in the smartphone's configuration. An example of this is the total traffic just measured 1 week ago, the last measurement, in the 4 big cellular networks in US. So the big cellular networks in US, Verizon, Sprint, AT&T, and T-Mobile all together already surpass 70% IPv6 traffic. So IPv4 is becoming nothing in just maybe 1 year, okay? As soon as more and more content providers move to IPv6, all the traffic will be IPv6 only. Now, let's suppose in your network you provide, in addition to IPv6 cellular services, you have other ways to connect your customers, maybe GPON or DSL or whatever other technology. Why you are going to use DS Lite for your DSL customers or your GPON customers and 464XLAT for your cellular? Use the same for all of them. Just make sure that your CPEs, whatever access technology you have, support 464XLAT. Basically, they need to support this size of code, which is open source. You just ask your vendor, or you provide it, or I switch to another one. That's easy, okay? I understand that for existing CPEs, it may be not so easy. You need a firmware upgrade, but think on this. If you start replacing CPEs or whatever, make sure to ask for CLAT support to your vendors, okay? So you have a single multi-service network with a single transition protocol instead of having several of them. It's ridiculous because in cellular, you have no other way than going to 464XLAT, right? I think everybody's clear about that right now. And this is an example of a single customer. I said here, user network. In this side, that's the user network, and this is the ISP. This is a real setup that I am doing for demonstrations, and I am running the NAT64 and the DNSSEC in Ubuntu virtual machines. So I have an Ubuntu virtual machine supporting Bind for the DNS and Joule for the NAT, and then I have the complete plat, okay? And then I have another virtual machine or a small CPE having support for CLAT. I am using OpenWRT or Joule, depending on how I want to do the demonstration. I have even that set up in my laptop to run all this in my laptop, okay? Some of you maybe have participated in the last week workshop. I was doing a demo about that, okay? So this is the way, 464XLAT for any kind of network. Even the tutorial was meaning just for cellular networks, but I don't want to avoid taking the opportunity to show that this can be used as well for all kinds of networks. And with that, we are done, I think, right in time. 1 minute late. Questions? Just 5 minutes. Anyway, I am here the rest of the day if somebody wants to grab me at any other time. So can we go to the exam now, or everybody got it clear? Okay, no questions? Yeah? Mike, please.
Thank you for giving such an inspiring tutorial. I must say I learned quite a new idea here. And sounds very confident to remove the dual stack solution. So there is one
point here. Removing in your access network, maybe in part of your core network, but not in the edge. The edge should keep dual stack. That's very important.
Yeah. So there is one more thing I would like to make sure. So your suggestion is that we don't need any tunneling solution, including 6RD, DS Lite. Let's remove them.
Remove all them.
Okay.
Just make your network much simple.
Yeah, simple.
You just need to get the CLAT support in your CPEs. Done.
Okay. Thank you.
Thank you very much. So thank you again. Let's go.